Okay, so I will continuing discuss this problem of algebraic integrability of essentially foliations on the plane. Let me start by recalling the conjecture. Which appears in a joint work with Roberto Esvaldi. So it says that the Zariski closure of the set of degree D foliations on P2 which are algebraically integrable, meaning all leaves algebraic, consists of transversally projective foliations. So let me start with some examples. So the very first example was already worked out by Enrica, which is if I have foliations of degree 0 on P2. So these are, they're essentially, there is up to automorphism, there is only one foliation like that. And it's the pencil of lines through a point. Remember the argument, so you know that by definition the degree is the tangent with a line, the number of tangencies. So if you just take a leaf and you take the tangent line to that leaf, it has a tangency because it's the tangency line, so it must be invariant, it cannot be not invariant. And you work a bit, and you see that we have all lines should pass for, all leaves are lines, and they all have a common point. So the second example is foliations of degree 1. And here, perhaps it's nice remark that the canonical of the foliations of P2 minus 1. And the second examples, foliations of degree 1. So here we are in the situation where the canonical is trivial. And if F is general, then the number of singularities is 3. And they are in general position, so you have 3 points on P1. And again, you can look at the line passing through 2 of them. We are going to have tangency at the singular points. So here, this line has tangency at least 2. But the degree, which is the number of tangencies, is 1. So this means that this line is invariant. And the same way, the other lines are invariant. And you end up with something like this. And now it's a trivial matter to verify that this foliation is defined by one form like x dy minus lambda y dx. lambda in C star. And they all have trivial canonical bundle, but then F will have reduced singularities. If and only if lambda is not rational. We don't need to worry with the sign because even if if lambda, which is the quotient of eigenvalues of the vector field, here is positive, there will be another one which will be negative and vice versa. So at the end, I'm not claiming that this singularity is reduced if and only if lambda is not a positive rational number, but if this is lambda, the other one will be written in function of lambda. Okay? Very good. I'm just looking at any foliation. Here is any foliation of degree 0 is like that. And I'm describing the general foliation of degree 1. It will be like that. And all leaves will be algebraic, if and only if, again, lambda belongs to Q. So in this case, let's call this F lambda. And then F lambda is algebraically integrable. If and only if lambda belongs to Q.
What are the leaves in that case?
The leaves are the solution of this differential equation. You can write this in another form. You can write this as dy over y minus lambda dx over x. And this is the differential of log y minus lambda log x. And so you see that you have a multivalued first integral of the form y x lambda. And then the leaves will be y x lambda equal to constant. This?
Yes, this is still under the assumption that F is general.
Yeah, that's in this case. But if it's not in that form, what is happening? Yeah. Either there is a saddle node appearing, and then it is not algebraically integrable, because a saddle node does not have a meromorphic first integral, or so indeed the ones which are algebraically integrable are this. Okay, so let me give one perhaps more involved example, which I mentioned already yesterday, but let me give some details, which are these Lins netus examples. So it will be a pencil of foliations of degree 4. So let's start with let's look at the following thing. Let's look at the pencil x3 minus y3 divided by y3 minus z3. So this is as you can see, it's a pencil of cubics, and it's quite clear that the general element, it's a Fermat cubic. It's an isotrivial family of cubics, which has two special fibers here at least. But then if you just consider x3 minus y3 plus y3 minus z3, you get x3 minus z3. And so you have, indeed, 3 special fibers. So every other element of the pencil, every other fiber of this rational map will be a Fermat cubic, will be isomorphic to x cubed, y cubed, z cubed. Okay? And now here there is a very nice, this is a very nice arrangement of lines, which appeared in many different situations. And so you have, this pencil has 9 base points, and through each of these 9 base points, you have 3 of the lines passing there. And if you blow up, you end up with the following configuration. So I'm going to blow up these points, and I will also blow up the base points of the pencil, the 9 base points. And so these guys will be -1 curves, and this will be -3 curves. Okay? And here the general element, the general leaf will be a Fermat cubic. And now, one thing that you can do, you can apply the standard Cremona to F. So let's call F0. Let's 0. And we can just apply here, right? So I'm sending x, y, z to y, z, x, z, x, y. And that's the case. I can just apply here to see what's happening. So this will be y, z cube minus x, z cube divided by xz cube minus xy cube. And here I will have a z cube, which will get out, and will remain y cube minus z cube. And I will have x cube, which get out, z cube minus y cube. Okay? And surprise, this foliation, so this foliation here, let's call F1, is also degree 4 foliation. Which has which leaves invariant the 9 lines that I just wrote here plus the coordinate axis, x equals 0, y equals 0. Let me just check here that the degree is actually 4, right? Because here, what's the situation? What's the normal bundle? The normal bundle is just OP2 2 times the degree of the fiber. So D is equal to 4, right? As there are no multiple components in the other fibers. In this case, you can try to do the same computation. And at the beginning, you may think that the situation is off, because now it's a pencil of sestics. So the normal bundle will be 2 times 6. But I have exactly 3 non-reduced fibers. In each of these 3 non-reduced fibers, there is a line with multiplicity 3, so this should be minus 3 times 3 minus 1. All right, so this is 6, it's the degree of the fiber, general fiber. And this is the number of non-reduced fibers. And this is the degree of the fiber minus the reduced fiber. This is a special fiber minus the reduced special fiber. And so here again, you get 12 minus 6, which is again 6. And so the degree is 4 again. So we have these two foliations of the same degree. You can write down explicit equations without problem. It's easy to see that they will have radial singularities at these points. So these are radial singularities. For both F0 and F1. And this point will be a non-decritical singularity for F0 with algebraic multiplicity 2, while it will be a radial singularity for F1. Okay? And now, so let's assume that this guy is defined by a one form omega 0. And that this guy is defined by one form omega 1. And then what we can consider is the pencil Ft, which will be T omega 0, or lambda mu, lambda omega 0, plus mu omega 1. So this is the pencil of degree 4 foliations. And in this situation, it's quite nice to do the computations, a pleasant experience. And you are going to verify that you can look at Kf, F to 0, so let's call the foliation that we obtain after blowing up these 12 points F to the 0, and this is reduced, and the Zariski decomposition will be, so if I call these guys E1 to E9, will be sum I equal 1 to 9 of 1/3 EI. Okay? And now if you remember the proof of this theorem that Henrique explained us yesterday, we can construct in this situation a 3-to-1 covering. So there is this blow up of P2 in these 12 points. And then there is a generically 3-to-1 map from surface S. And what turns out is that the surface S is just the Fermat cubic to the square. It's birational. I'm not saying that it's isomorphic, it's birational. F tilde is the foliation obtained here after blowing up the 12 points. It's the foliation on the blow up of P2 on these 12 points.
And the 9 points are those?
Are the base points, and I'm also blowing these up because here, if you compute the
The sum is only on 9.
yes,
Is that only the 9 square?
yes, I'm not blowing up in these points. Okay.
The P, are you specifying what P is, or it doesn't matter?
What?
P, the positive part.
P is, in this case, P is 0. Q. P is numerically 0. Okay? And it's very interesting that this is the Kronecker or Abel foliation as I explained it yesterday. So this Spencer's Kronecker Abel foliation. And so in this case, by this result of Abel, the foliation will have a rational first integral. All leaves are algebraic. If and only if lambda over mu belongs to the Q times the endomorphism ring of this curve. And so if and only if this guy belongs to Q. So Q, primitive root of the unity. In particular, for a dense set, we have algebraic leaves. And for the general element, the only algebraic leaves are these 9 lines. You see, so in this family, I'm also considering a pencil here. We have the set of foliations which admit an irrational first integral. I'm looking at a subset of C. It's just the rational numbers. And here, it's more complicated. It's even topologically dense. Is this Q, cubic root of 3. Very good. But in all these examples, there is one common feature. We can ask, well, what your conjecture is saying in these examples? It's saying essentially nothing, because in all these cases, everybody is algebraically integrable. Here, everybody is defined by a closed rational one form, in this case, like here. So everybody is what we call transversally Euclidean. And in this situation, after a finite covering, everybody is defined by a holomorphic form, so it's also it's transversally affine or virtually transversally Euclidean. So in these examples, this phenomena is verified. And you see, in both case 2 and case 1, the general leaf for the algebraically integrable foliation is not bounded. The degree is not bounded. But the degree of the integrating factor in both families is bounded. So here the integrating factor will be 3 lines, and here will be 9 lines. And you have this. And another last remark about these examples is that here the singularity is moving, right? The singularity depends on this lambda. This lambda is the invariant of the singularity. There is something happening when we move the parameter. But here, in these examples, you can write down equations, and if you look at singularities, nothing is happening at singularities. They are not moving. The analytic type, the combinatorial type, is not moving generically. There will be a few parameters where this phenomena will happen. But for the general element, the type of singularity is constant. So if you want to understand more dynamically what is happening, at least in this picture, so you have, since this is the negative part, there is only one singularity. The connected components of the negative part have only one curve. So as was explained yesterday, they will have only one singularity. And then when you move the parameter, these singularities will move. When they move just a bit, this curve will be destroyed. But then in a dense set of parameters, there will appear another -1 curve here, but with degree going higher and higher and higher and higher. So this is a very nice example. It's very symmetric. If you can, yeah. But then there was a student at a student of Lins Neto at IMPA, Liliana Picciuri, who wrote the degree of the first integral as a function of lambda over mu. So even if you cannot bound just in function of combinatorial data with the equations, and you can write down the degree of the first integral. Okay? Very good. I would like to recall now another result of Poincaré, which appears in that paper. So let me just write down one thing that I mentioned yesterday. There is this standing assumption through the whole paper of Poincaré, which says that all singularities have invertible linear part. And let's write down mu if P belongs to sing F. Even we'll only look at the critical singularities. So these are those singularities which look like base point of pencils. Let me write down mu P over nu P for the quotient of eigenvalues. And then, I think I can state the theorem here, theorem Poincaré. And so let F foliation on P2 of degree D satisfying H. Assume F is algebraically integrable. So every leaf is algebraic. And let C be the general leaf. Then we have the following formulas. C square just call this dic F. It's just R P C. So this is the number of branches of C through P times mu P nu P. Okay? And B, the normal bundle of F times C. Of course, Poincaré doesn't talk about the normal bundle. He just writes D plus 2 times C is equal to the sum P the critical of F RP C times mu P VP. And C, the genus, the geometric genus of C is 1 plus sum P. Rp over 2 nu p plus mu p times kf dot c divided by, let's call it d minus 1, d plus 2, minus 1. Okay? Very good. So the proof of this result is, if you want, RPC. So RPC is the number of branches of C through P.
Degree of NFC, or is
Sorry?
in formula B, this number at the on the left hand side?
NF is a line bundle, C is a curve, and intersection number.
Okay.
Let me just write down a corollary. Degree of C divided by 2GC minus 2 is at most KF divided by MF, and small kf divided by big MF, where MF is the minimum and M is the max of the same formula, and small kf is the minimum of mu p plus mu p divided by degree of f. Oops. Plus 2. And big KF is the maximum of this, the same number. And then, so if MF is positive, then we have this. Okay? So let me just, I think it's completely fair, at least this result, I'm not saying that this result is trivial, but it's fair to say that it's an exercise on the intersection formulas that Enrique showed you. And indeed, he proved this, and essentially he claims, he asks if there is a general formula for the case without algebraic first integral, and the general formula would be really these intersection formulas, the Poincaré-Hopf and then NF. So this is an exercise on the formulas, NF.C, KF.C. There's not much more than that. And the Theorem, whatever. Okay? And then to go from here to here is just algebraic manipulation with this with these equalities. And as you see, if this number is positive, then you get something. But let's see the simplest case possible. The simplest case is when for every p in dic F, we have that mu p equal nu p equal 1. Indeed, Poincaré in his paper only deduces the corollary for this formula, but then it's easy to see that what you have in this particular case. In this case, what we are saying? We are saying that if 2 times degree of f minus 1 divided by degree of f plus 2 is greater than 1, right? And so we are saying that
Sorry, could you read the thing in the brackets in the definition of lowercase n f?
here,
Yes.
so it's mu p times nu p plus nu p, which are this quotient of eigenvalues, times degree of f minus 1 divided by degree of f plus 2 minus 1. K is nu p plus mu p divided by degree of f plus 2. See, so in this, if only if degree of f is greater than 4. So, in this simplest case, where all the critical singularities are just radial, Poincaré is giving a bound of the degree of the general leaf as a function, in function of the genus of the general leaf.
I'm missing the point in this definition. So if you divide m of p by k of p, so the only thing that depends on p is essentially the same. So if you, I see, because you are dividing maximum by minimum, is that the idea?
Yes, yes.
So you could,
No, but maximum by minimum, and they are interchanging. Here's maximum of k divided by minimum of m, maximum or minimum of k divided by maximum of m.
so they are both essentially kind of inverse of one another or something?
No, not at all. This is big, this is small. So k is different from.
Is there a way of understanding this invariance so they have meaning?
That's one thing that I asked for 10 years, and I think I found one and I tried to explain. Not exactly those invariants, but what this thing is saying, because I couldn't understand for a long, long time. Yeah, it seemed very mysterious to me. I couldn't give some high-level explanation what's really happening. And the thing that somehow, so it's an exercise, and just try to keep this. It's saying that under some conditions, which can be checked, I'm giving, or Poincaré is giving, a bound of the degree as a function of the genus. And in very concrete. It's a very nice result, but with the drawback that you have to assume something very strong about the singularities. To be algebraically integrable is a degeneracy phenomenon. It doesn't seem fair to study algebraic integrability under non-degeneracy assumptions. So, anyway, and the point is that while looking at this and observing that the problem of deciding or knowing if a foliation has algebraic integral or not is a birational invariance, I think that we should try to understand these things under the light of the birational geometry. And it would be nice to give a birational interpretation of this result, right? And in particular, try to extend this kind of results for the case where all the singularities are arbitrary. To try to formulate this kind of statement in a birational way. And so that we could do, and let me just state a theorem. Which somehow can be seen as a generalization of this corollary. And so let f algebraically integrable foliation on P2 of degree d. And let's assume that f is non-isotrivial. F is birationally equivalent to a non-isotrivial fibration of genus G, at least 2. And then the degree of the general leaf, we are aiming at something close to that, is at most 4 times 42 times 2 genus of C minus 2. So I have closed this 42. And then I put a factorial here. Why not? And then square 4g minus 4 degree of f. And so you see, well, of course, this is much better. It's linear. And this is very far from, it's linear on the genus. This is very far from linear. But still, it's something which only depends on the genus. And so there is also, under the same assumptions, under the assumption age, if the degree of f is greater than 4, then we have a sublinear version with the same method, sublinear version of Poincaré theorem, of this corollary. So let me try to discuss some of the ideas of the proof, or the idea of the proof, idea. So the point is that non-isotrivial fibration so let G be a reduced relatively minimal model for F in the sense of Enrique's talk. So we produce G from F by taking a resolution of singularities and then contracting the -1 curves. And so let G be like that. And so if we are in the situation that we have a non-isotrivial fibration of genus at least 2, then I think this is a theorem due to Serrano, perhaps some. Then we have that Kg is big. So the sections or powers of Kg grows quadratically on the power. So this. Okay. At the same point, if C is a general leaf of G, since we are assuming that we are in the fibration case, when I restrict to this general leaf, when I look at this general leaf, there will be no singularities of G on it. And when I restrict Kg to C, I obtain nothing but Kc. Just because sin G intersection C is empty. Okay? And so if I look at the restriction morphisms, we know that this guy grows like n squared. We know that this guy grows like m. And so we can, in principle, if we have some control when this guy has three independently algebraically, when it has three algebraically independent sections, we have some control of when the kernel will be non-empty. So if n is large enough, then the kernel of non-empty. And so we have sigma in H0 Kj tensor n such that sigma restricted to C is equal to 0. But now just let's see what we are doing, right? So we started from P2, and then we went to this surface S. I had F here. I have G here. Well, let's just assume isn't have this, right? Because we contract something, right? But anyway, one thing that you can verify is that if you push forward this section sigma, it will be a section of H0 P2 Kf tensor n. But Kf tensor n is OP2 d minus 1 times n. So if we know n, then we have a polynomial of degree d minus 1 n vanishing on C. So this is a bound for the degree of C. Okay? But the problem is to control n. So how to control n? I have no idea. And I think it's like a very nice problem. You see, if you try to, if you think that these foliations are objects similar to surface, are generalizations or are versions or are variants of surface or projective varieties, you can ask all the questions that people in birational geometry ask in algebraic geometry for these objects. In particular, it seems to be really, really interesting to understand the growth of this guy as a problem by itself. But in the surface case, for instance, we know a lot about this. We have theorems by Bombieri, which says when the sections appears, and we had further and further refinement. But in the case of foliations, we have nothing at all. And this seems to be useful to this problem and perhaps to other ones. I did 17 years ago and got stuck, couldn't. I kept asking for people from birational how to do that, But then Roberto had this come with a very nice idea, which is the following. So a foliation doesn't have only one canonical bundle, right? We are writing canonical, but the conormal is also canonical, right? It's something that comes intrinsically attached to F. And the point is that you can try to look not only to powers of Kf, but you can try to look at powers of Kf combined with Nf. And in the same way that Enrique showed to you that the H0 of powers of Kf is a birational invariant, H0 of these combinations are birational invariants, right? And the point is that since we know that Kf tensor n star f is just Kx, to look at this kind of combinations is the same thing as to look at this kind of combinations. And for track this problem, there is technology. So the technology, the usual technology is to look at this kind of problem, right? It's there where we have technology, where we have results, and we can obtain effective results on when the n appears. Very good. But still, the general problem, which I think is just control the growth of these things absolutely, without assuming anything, we still don't know how to do. But the thing that we are going to explain how to do is in the case of this fibration, of genus G fibration. If I control the genus, so what I want to do. So the point is the following. So there are theorems that say that, well, if I have L, a big an F-line bundle, then there is this theorem of Heider, which says that Kx tensor L tensor 4, this linear system defines a birational map to its Z. Defines a birational map from the surface. So here is for surface. Smooth projected surface. Okay? Very good. So that's what we need to do. We need to cook up the big and F-line bundle. But in our situation, we are quite close to that. We have big, but we don't have Nef. But Francesca explained Enrique. Anyway, so we have the technology to do that, to replace a general big line bundle by a big enough line bundle. It's the Zariski decomposition. It's done to do that. Very good. So we are in good position. We can apply this thing to P and control everything. But there is still a catch. I need to be a line bundle. It needs to be a divisor. And Zariski decomposition is for Q divisor. So we need to be able to bound the denominators. We have to control the denominators of this guy. And that's controlling the denominators that this factorial and things appear. It's there where we lose. Perhaps there is a way to get rid of that factorial, but let me try to explain how to. After saying all that, the things we have reduced to is to, the time is over, almost. So it's so we have to control denominators of the negative part. Okay? And it's not hard. It's essentially the point is the following. So you have, let's take a fiber. And let's look. I want to compute P times T, where T is a component here. The thing is that if T intersection with the support of N is empty, then P of T is an integer. And using Liouville inequality, we can show that it's at least 1. And so the tricky part is when it intersects the negative part. But we have the very precise structure of the negative part. And the point is that we know if intersects the negative part, since the negative part is invariant and T is also invariant, it must intersect in the tail of the negative part. And we know how to compute the intersection with the tail of the negative part, and we use something like 1 over O, where O is the order of the cyclic quotient singularity. And so all this allow us to show essentially the following. If P of T is equal to 0, then indeed the fiber will be just T plus 2, so this will be the support of N. And you're going to deduce that the fiber itself is elliptic fiber. So does not fit in our setup. And in any other case, P of T will be at least 1 over 42. 1 over 42 is, of course, the volume of the orbifold, the hyperbolic orbifold with the smallest possible volume. It's the kind of constant that appears in all problems like that, right? It's how like that you bound the order of automorphisms and so on. And so with that 42, which is the same 42 it's appearing there, you can do this and control effectively powers where these things appear, and you prove that eventually. Okay? And there is another very nice feature, unfortunately we will not have time to discuss, of these invariants, is that they are much more relaxed invariants with respect to singularities, right? One big problem of the traditional birational invariants is that they do not work well in family. Because it's not that the invariants do not work. If you have a family of reduced singularities, they do work well. They do behave well. But the problem is that when you take something like that, you cannot resolve in family because you have to take care of all rational numbers, and when the rational numbers are there, you have to do more and more blow-ups. And the point is that as soon as you add a bit of positivity in this side, you don't need to resolve all rational numbers. You only need to resolve a finite number of them, because the concept of canonical singularities for these line bundles are less restrictive. And so this opened the way to do arguments by Noetherian induction, something that we cannot do with the usual invariants. And doing Noetherian induction is how we prove. We have to use that result and use a classification in function of the growth of these things, like Francesca, like Enrique will explain later today. But she will explain the classification in function of the growth of these invariants, but you can do as an exercise a classification function as a function of these invariants. And you use these ingredients together with Noetherian induction, which now we can do because these guys are cooler than the KF. And you can prove this, not the conjecture, sorry. You can prove a version of the conjecture. The result that you can prove is the following. Let me just state it then before finishing. We can prove, let me write it here. So the set fix G natural number. The set of foliations with the Zariski closure of the set of foliations with general leaf algebraic of genus at most G consists of transversely projective foliations. So unfortunately, I need to control the genus. I have to fix the genus. I don't know if everything is transversely projective, but if we fix the genus, we have, and this is as far as we got in this conjecture. Okay, thank you. Sorry for the delay.